Hello everyone, welcome to another video demonstration. This time we're looking at the optimal RQ policy, also known as the optimal reorder point model. Remember, we're using this model when we deal with uncertain demand and uncertain lead time. To do this, we need to expand on our basic EOQ model and include a safety stock, which ultimately translates into using a reorder point. In other words, our order policy is now defined by two parameters, that is the order quantity Q and the reorder point R. Now I want to discuss this policy in the context of problem 13, taken from the POA textbook chapter 5. So in this problem, we're given data for an automotive filter, if I remember correctly. All that matters for us in terms of the analysis is we need demand and lead time information, which we have here. So lambda is 280 units per month. The standard deviation of demand is 77, so that tells us that demand is in fact a random variable. And we're going to assume here that it is normally distributed. The lead time is 5 months in constant. We know it's constant because the standard deviation of lead time is sigma sub tau is 0. We are also given cost information, that is the holding cost factor, I, the unit cost, as well as the stockout cost. Since there is uncertainty involved, there is the possibility of stocking out, and there is a cost associated with that, and that is the backorder cost P. Again, that's a unit cost for every unit that we stock out by. Notice that we're making the assumption here that the demand in case of a stockout is not lost, it's simply backordered. And there's a cost associated with backordering. There could be a cost of expediting, an extra transportation cost, the cost of giving a rain check, the cost of upgrading, for example. And then of course we have the order cost. So I'm going to show you here how we can easily define the inventory control policy that will again minimize total cost. That is always our objective. Now we can actually do this in multiple ways, and I want to show you two different ways of implementing or finding the policy. Of course, no matter what way we do it, we have to come up with one and the same solution. So I'm going to start out by showing you the easy way, and I always like the easy way, of course. And what I'm going to do is I'm going to complete this worksheet from top to bottom. And I recommend you always do the same thing. That way you really can't go wrong. So as for the order quantity Q, I will start out with some arbitrary placeholder value, and I'll just pick 200 units. Again, it doesn't matter what I put in here right now. You'll see here in a little bit why it doesn't matter. Now let me scroll down and look at annual demand. The reason I'm calculating annual demand is I got to be careful later on in my formulas that I don't put apples and oranges into the same formula. Because demand here is given on a monthly basis, but notice also that holding costs, for example, are given on an annual basis, I need to make sure I always measure everything in the same increments of time. I will calculate annual demand, of course, simply as 12 times average monthly demand. Now, as for the type of service level alpha, again, I will start out by putting some placeholder value. For right now, let's say 90%. Again, it doesn't matter what we really put here. I will explain later why. I'm just putting in some random number here. Now I will also calculate the holding cost, which is, of course, as always, I times C. So in this case, my holding cost per unit per year is 42 cents. So I have the backorder cost. I have the order placement cost. Now I need to calculate the standard deviation of demand during lead time. Remember, this is my measure of uncertainty, the convoluted combination of demand and lead time uncertainty. We can simply calculate it using the Excel formula that you see given to the right. So because I'm lazy, I'm simply going to go ahead and copy this formula. Just remember what this actually means. It's the square root of average lead time multiplied by the variance of demand. And I'm adding it to the product of average demand volume squared multiplied by the standard deviation of lead time. Again, you got to make sure you measure everything within this formula in the same increments of time. In this case, everything is measured on a monthly basis. Again, we would get that exact same value if we were to convert all of the information on demand and lead times into an annual level. Either way, the standard deviation of demand during lead time is unit-free, and in this case, it is 172.18. Now, the mean demand during lead time is actually easier to calculate. It is simply average demand times average lead time. Well, the average lead time in our case, which is mu sub tau, is 5 months. And the average demand per month is 280, so average lead time demand is 1,400. Next, I calculate the standard normal variant. That is the value of z that corresponds to the, for now, arbitrary value of alpha. and I calculate z as norm's inverse. And I use the norm's inverse function here because I'm assuming a normal distribution. Remember that for Mac users it is norm.s.inv, and for PC users it is normsin. I am assuming that the demand during lead time is normally distributed. If that is true, then I can convert the probability of being in stock into an associated number of standard deviations to go above the mean, as to cover the desired area of alpha under the normal distribution. With that being done, I can now calculate my safety stock requirement as z times sigma. Right now, I'd be looking at 220.65 units of a safety stock requirement. Now here's the wonderful thing about Excel. Excel actually allows me, given, of course, a number of assumptions, to estimate the average number of units out of stock per cycle, and that's what we call the N of R. So given the statistical properties of demand and lead time distributions, and given our desired type on a service level of 90% for now, I can figure out how much an average I would stock out per cycle by implementing the formula that is shown here on the right. I'm not going to get into the great detail explaining it right now. My point is, given the numbers you see on the screen, we should be stocking out by an average of 8.15 units per cycle. That, of course, is simply because alpha is 90% and not closer to 100%. In fact, you see that if I change alpha to 98%, you would, of course, see that N of R, the expected stock out quantity, decreases at the same time, of course, as the safety stock increases, as a result of the greater in-stock mobility. Again, we are not worried about the specific numerical values right now. Now that I have a value of N of R, I can also determine the associated fill rate, which would of course be 1 minus N of R divided by Q. So with an in-stock rate of 98%, I would obtain a fill rate of 99.4%. Now finally, my order point is, of course, the sum of average lead time demand and safety stock. So now you see I have defined an RQ policy. That, of course, hinges on the assumption that my order quantity of 200 and the alpha of 98% is indeed correct, which it may or may not be. So last but not least, what I'll do is implement the total cost function. I'm doing this here step by step, so I'll start out with the cycle stock holding cost, which of course is Q over 2 times H. And then I'll calculate the safety stock holding cost, which is safety stocks multiplied by H. My order placement cost, as always, is equal to annual demand. Now be sure you use annual demand, not monthly demand. Annual demand divided by Q. That gives you the annual as opposed to monthly demand of order placements. And I multiplied that by the order placement cost K. And finally, we estimate the backorder cost, the annual backorder cost. Now remember that the stock out quantity per cycle, N of R, is again the stock out quantity per cycle, and I need to multiply that by the number of cycles. Well, the number of cycles is, of course, again, annual demand divided by Q. And now I want a cost figure, so I multiply this with the stock out cost per unit P. So I get my total relevant cost, G of Q. That is the sum of these 4 constraints points. So right now, given the number on the screen, we'd be looking at a total relevant cost per year of $2,142. As always, the question, of course, is, can we do better? And the answer will, of course, be yes, simply because, remember, I use these random values for Q and alpha. I don't actually know whether they are truly optimal or not. Now let me find out by using Excel Solver. And that's the easy way of optimizing here. So I want Excel to minimize total cost. And my objective function is G of Q and of R. And I want to minimize that by changing 2 values at the same time. That is Q and alpha. Remember that alpha in turn defines safety stocks, which in turn defines the reordering point. Now it is customary in this case, and actually mandatory really, to implement a series of constraints. Specifically, I want to make sure, of course, that my order quantity Q is equal to or greater than 0, or let's say 1, for practical purposes. I want to order some positive amount. Also, I need to impose a couple of constraints regarding alpha. Now, technically speaking, alpha can never be 100%. Remember, if I want to make sure to obtain a service level of 100%, I would need to hold an infinite amount of safety stock, so as to make sure I never stock out, which of course is practically not feasible. So I constrain alpha to be equal to or less than 0.999 and a couple more nines if you want, but it cannot be 1. And also for practical purposes, again, it may make sense to make sure you have an in-stock rate that is greater than 50%, so greater than 0.5. If you ever are in practice achieve an in-stock rate less than that, you're probably not going to have your job for very long. So for practical purposes, we typically want to achieve in-stock rates that are well above 0.5. So now I click OK, and what you see right here is my constraint optimization problem. Again, I want Excel to find the values of Q and alpha that will minimize the grand total cost of G of Q and R, subject to the constraints that Q be equal to or greater than 1, and that alpha be somewhere between 0.5 and 0.999. Now I click on the solve, and you can see I get an optimal solution. That this optimal solution is Q, which is 1,326, and alpha in the optimum should be 98.7%, which then implies that I would have a safety stock holding of 384 units roughly, equating to a reorder point of 1,784 and resulting in the fill rate of 99.9%. So this answers part A of question 13. Part B asks for the holding cost, the setup cost, and the stockout cost associated in the policy. Well, of course, these are the values here. Notice that they have two holding costs, cycle stock and safety stock. So if I sum them up, I get $439.63. That's the holding cost. The setup or order cost would be $253.32. And the annual back order cost is a very low $25.21. That, of course, is because I achieve a very high fill rate, and I have a very low number of stockouts per cycle, and also a fairly low number of cycles per year. So I simply don't stock out by much, which is why the value is so low. So this answers part B of question 13. To answer part C, I will refer you to the second video, which we are going to answer that part of the question, and I'm also going to show you an alternative way of evaluating or determining optimal inventory control policy. Of course, the solution will be the same. I just want to show you another way of finding these solutions. For now, thank you for watching, and please come back for more in part 2.